Welcome to the AMSOIL Technical Information Series. In this segment, we're going to talk about some of the differences between mineral and synthetic base fluids on there. Give you a general overview. First of all, we have to realize that changes have occurred, and they always will occur. And it's certainly, or I should say, automotive applications are certainly no exceptions. Today's equipment is significantly different than what we saw just even a few years ago on there. And the lubricants that were used 5-10 years ago, in many cases, probably aren't adequate to take care of the needs of the equipment that's available today. What type of changes have we seen? Well, we're seeing a lot greater horsepower out of the smaller engine sizes out there. We're seeing turbocharging being added to many engines. Why did they do that? Try to increase volumetric efficiency and get more horsepower, more ponies out of smaller engines. Direct injection fuel delivery, totally different than what we saw in the past. Causing issues with fuel dilution and this type of thing. Emission systems, emission recirculation. In some cases, many cases, what we're doing is we're taking exhaust gases and actually recirculating them back into the combustion chamber. And this is putting more and more contaminants in there, creating heat issues, creating deposit issues, things that we never really had to concern ourselves with in the past. Lean burn engine designs. Lean burn engine designs or technology is used to try to improve fuel economy. Unfortunately, by doing that and running these leaner air-fuel mix ratios on there, engine operating temperatures are going up. Aerodynamic changes to the equipment itself. If you can remember back in the good old days, back in the 40s and 50s, the front grills on the cars that were running around at those times were huge. My word, you could pass birds and small children through them. They're so big, allowing a high level of or a high volume of air to pass through and cool the engine and drivetrain on that. Nowadays, very small frontal areas, very small openings to minimize the air that's passing through or underneath the car itself. Again, this is all increasing operating temperatures within the components of the vehicle. To give you an example, back in the 70s, the temperature underneath the hood averaged around 170 degrees. In the 90s and 2010 era, those temperatures increased, average temperatures increased to over 225 degrees. And if you remember, if you look back at what you learned on lubricant fundamentals, you know the rate of deterioration of a product will double for every 10 degrees increase in temperature. So not only are we heating everything up to a higher temperature in the engine, but now our lubricant that's in there that is trying to combat these issues is deteriorating at a more rapid rate. So all of these things are causing issues. Also too, if you go back 15, 20 years, you know, oil never used to last much more than 3,000 to 5,000 miles in a car. Matter of fact, the OEMs, original equipment manufacturers, always said, hey, change your oil every 3,000 miles. Kind of a rule of thumb, right? Conventional oils understand what they're saying here. Nowadays, however, we can see owner's manuals basically saying, don't worry, the car is going to tell you when the oil needs to be changed. And sometimes that change is 5, 6, 10, 12,000 miles down the road. So not only we're exposing that oil to higher temperatures, higher loads, more contamination, we're saying, you have to do these, you have to meet all of these issues, and you have to be able to remain in service for significantly longer than you ever did before. Also too, we also know, looking back at lubricant fundamentals, that the thickness or the grade of the oil, its viscosity, or I should say load carrying ability, is directly related to that grade, that thickness of the viscosity. The heavier it is, the oil is, the greater the load it can carry. But what we're trying to do now in an effort to improve fuel economy, we're putting lighter and lighter oils in the engine. So these lighter oils have less load carrying ability. Okay, so we're putting the oil in a real questionable state. You know, can the mineral oils that have been common for years and years really deal with all these new changes? Really deal with these more severe type situations and issues? Well, again, when we look at conventional oils, mineral oils on there, we know that there's a lack of molecular uniformity. I always like to say they're more like vegetable soup. There's a whole lot of things in there. The soup as a whole is pretty good. Okay, I kind of prefer the meat and potatoes. Corn's okay. The lima beans and the onions, though, they're not my favorite. Okay, they don't meet the type of appetite that I have. And mineral oils are kind of the same way. They got a lot of meat and potatoes in there. So they're doing the hard jobs, lubricating, cleaning, all of this other type of stuff. But the lima beans, or the contaminants that are in mineral oil, really aren't helping out at all. If anything, they're detracting. Okay? There's a lack of molecular uniformity, and contamination can be an issue on there. Plus, too, when we look at mineral oil, comes from crude. Depending on where it's obtained, its molecular makeup is going to vary. So again, its ability to address issues is going to change, all depending on where it came from. Was this some Texas sweet? Did this come from Saudi Arabia? Is this from the North Sea? They're all going to be slightly different, slight variations in there. And they do have a tendency to degrade at significantly lower temperatures, okay? With the issues that the new equipment are being faced, this is a real detriment. Alternatives would be what is commonly referred to as a synthetic. And you have to remember, synthetic is a very generic term, and it refers to nothing more than a man-made substitute to a natural occurring product. We see it every day. We see it in the clothes we wear. Are all your clothes made out of cotton? No, we've got nylon in there. Well, nylon is a synthesized material, and it is replacing a natural occurring material, which is the cotton. The tires on your car, are they all rubber? Hey, I tell you what, if you want to get any life out of them, they better not be all rubber. There's a high percentage of synthetic materials in there that allow those tires to last significantly longer and function at a significantly higher level. So really, synthetics, as the general term is, are something that have been around for a long time. Now, when it comes to lubricants, fluid lubricants, it actually refers to a variety of different materials. Just like we talked about cotton and we talked about nylon. Nylon is only one synthetic for cotton. There's rayon, there's a whole bunch of other, other materials, synthesized materials that could replace cotton. As we talk about lubricating oils, there is a number of different materials that could be used to replace a conventional mineral oil. What's really the difference between the two? Well, mineral oils are refined and somewhat purified and changed a little bit to improve their characteristics. But like I said, they have issues. They have issues with molecular uniformity. A synthetic, because it is chemically engineered and designed from the ground up, has significantly better uniformity, which means when you look at a synthetic oil, if we take our vegetable soup conversation that we have, synthetics are all meat and potatoes in there. There is no lima beans. There is no onions in there. It's all good stuff. All good stuff that will assist the fluid in accomplishing the 7 basic functions of any type of lubricant. Purity, there's no contaminants. Crude oil has water in it, it has sulfur in it, it has other contaminants in it. Yes, some of that stuff is removed during the refining process, but it is not 100% clean. You've got contaminants in it as well. Synthetics, on the other hand, are contaminant-free. So there is a big advantage there. Less change with change in temperature. Again, when we get back to the fundamentals of fluid lubrication, we all know that fluid lubricants, generally speaking down here, their thickness will change with changes in temperature. As they're heated up, they tend to thin down, and their load carrying ability decreases. As the temperature decreases, mineral oils will tend to thicken up. Okay, and you'll say, hey, that's good because that increases their load carrying ability. A plus there. However, as it thickens, you run into a situation where now they become more and more difficult to circulate. And if you can't circulate the oil is not going to be where it has to be to protect the equipment components. So functionality over a broad temperature can be a real issue. Synthetics have a definite advantage there. They reduce degradation when exposed to elevated temperatures. Synthetics will not break down as fast, as rapidly, when exposed to these high temperature environments, especially the ones we're seeing now in today's automotive technology. So they're less self-contaminating, they can last and do their job for a longer period of time in more severe type environments. So a lot of pluses all the way around on it. Are synthetic lubricants something that are new? Actually, no, they're not. Okay, back in the 1920s, Standard Oil did a lot of research work looking at how they could develop and how they could produce a synthesized material that had this purity, had this consistency on it. It never went into commercial manufacturing with it, but they developed the technology for making this. Really wasn't until the 1940s when real production work, actual commercial production work occurred, and that was within Germany. They ran into a situation where raw materials were difficult to get a hold of, crude oil was, they had to look for some type of substitute, and synthetics were the way to go. They developed the manufacturing procedures for making these types of fluids in larger commercial type quality or quantities. In the 50s, in England, during the development of the jet engine, they ran into some real issues. They ran into issues of functionality at temperature extremes. At altitude, we're looking at sub-zero temperatures, minus 30, minus 40, minus 50 degrees Fahrenheit, okay? But they also looked at the temperatures at which many components within these jet engines were running. Very, very high, 500, 600, 7 degrees, or 700 degrees Fahrenheit. I mean, these were extremes way beyond any mineral oil could ever come near of handling. Now, there was some design changes that allowed them to address that, but what they needed was some type of substitute to the mineral oils that were commonly out there. And what they wound up doing is going with synthetic fluids in there. Matter of fact, even today, all jet engines that you see in airplanes utilize synthetic lubricants. Their mineral counterparts just cannot handle the demand of the application. When it comes to more the average consumer, where did they or when did they start becoming exposed to it was actually in the 1970s. AMSOIL itself being the first company to introduce and market an API-approved synthetic product. That kind of got all the wheels spinning. Matter of fact, shortly after that, other major oil companies came on. Mobil did shortly after that. Now we're to the point where virtually all major lubricant manufacturers offer at least some or one line of synthetic oils along with their mineral oils on there. And that's expanding too. A lot of work was done in Europe in the 1990s on what they refer to as Group 3. And it continues to change and progress on here. When we talk about consistency, let's take a look at the differences here. We've got a GC scan here of a mineral oil on the left-hand side, and you can see it's a bell curve. That bell curve suggests a variety of different molecular structures in there. Basically what you're looking for is ones that are the highest concentration, or one that's in the center of that bell curve. The reason for it, anything that's on the the left-hand side tends to be a very light fraction and has a higher level or degree of volatility. It also tends to oxidize or deteriorate at a much lower temperature and at a much higher rate, okay? So it's really not suitable for the high temperature environments, stressful environments we see today, or as suitable. If we go to the right-hand side, though, these are heavier fractions. What do these do? Well, these basically do a number of things. One, they minimize low temperature performance because they tend to thicken things up. Also, because of their thickness, they have a lot more internal resistance within them, and they tend not to be as fuel efficient. So here again, you don't want the stuff on the left or the right. You want to have the highest concentration of molecular structures that appear in the center. Now, if we look on the right-hand graph on there, this happens to be a synthetic, and it's what they call a polyalpha olefin, or Group 4 product on there. You'll see there is some variation in there, but very, very little in compared to our mineral oil comparison over here. We have a higher concentration of those molecular structures that tend to provide us with the highest level of performance. There's another thing too. When we take a look at the molecules in crude oil, they're not all perfect. They get beat up, they get bounced around, they get atoms knocked off and everything like that. They got holes in them, okay? But there's a bond there, an open bond, all right? Nature doesn't like that. So nature's going to try to find something else to take the place of that one molecule that was knocked off. Generally speaking, the most likely thing that's going to wind up there is an oxygen molecule. The molecule starts to oxidize. Once that happens, its properties, its characteristics change. It doesn't have the lubrication qualities that it had before. So this can be an issue on it. And again, when we take a look at synthetics, we don't have that. We don't have that issue, that problem of these partial molecules being in there. Again, I mentioned that when we're dealing with lubricants, the term synthetic is very general. It refers to a wide variety of fluids, okay? They're not all the same. They don't all have the same performance characteristics on them, okay? But they fall in this family of group on here. Probably the most dominant ones that you see out there today, first one in the upper left-hand corner is polyalpha olefins, or PAOs. We see them heavily used in the production of engine oils, so on and so forth. We see esters. There could be a whole variety of esters. Dibasic acid esters, polyol esters, phosphated esters, okay? They can be used in a number of different things. Phosphated esters are really, really popular when you're dealing with concerns regarding fire hazards or an explosive atmosphere. They tend to be used in situations where things like an explosion or a fire hazard could be a major concern. Underground mining would be one example of that. Polyisobutylene, that's one out there. It's used heavily in the production of two-cycle engine oils. Polyglycols up there, normally referred to as PEGs. We see a lot of use of those products in industrial type applications. Then we have what they call Group 3, and we're going to kind of define that a little more as we get on there. There is a large variety of synthetic options out there. Which one is used depends really on the need of the application itself, and it can and will vary. Here again, if we take a look and compare the different properties of these different materials, we see they changed dramatically. There is no one base material, mineral or synthetic, that scores a number one, which is best, in all categories. But you can see some trends there. Synthetics, generally speaking, across the board, tend to perform at a higher level than their mineral oil counterparts on there. And in some cases, to make a better product, you'll see synthetics or some synthetics out there that contain more than one base material in them, that are combinations, depending on the needs of the application. API, the American Petroleum Institute, has put together a generic base oil group classification on it. It tends to be based on saturation, the degree of or to what degree the most desirable molecules exist within the base material itself, sulfur contamination levels, and then viscosity index. And there we're talking about general functionality over a broader temperature range. The higher the number, the broader temperature range it can function over. Group 1 and Group 2 are mineral oils that are derived from some type of manufacturing process, usually refining process on that. They do have issues with uniformity and molecular structure. They do have contaminants like we talked about on there, and they really don't have the functionality over the broad temperature ranges. We talked about that when I brought up the example of jet engines. You know, they just couldn't handle it. Group 3 actually starts out as a mineral oil. It has been exposed to such a high degree and level of refining. By law, it can now, in most countries, it can now be classified as a synthetic. But it did have its start as a mineral oil. But it has been refined in so many different ways, gone through so many processes, it's been changed so enough, but utilizing the most general of terms to define a synthetic, it now does fall into that category. Okay? Group 4s are only PAOs only. Group 5s basically are anything else. Anything else. Most of them are synthetic, like diesters or PEGs, silicone, this type of thing. But actually anything else that doesn't fall in any one of the upper 4 categories, if it doesn't fall in those, it's going to be thrown into Group 5. So we have really a wide variety of things there. A couple of things to keep in mind. No one base stock group provides ultimate performance in all areas. So that's why in a lot of cases you'll see if it's a synthetic, most of the oils for that application may use one, where for another application they use another. Perfect example, automotive engine oil. You may see a Group 3 or a PAO. Jet engine oils. Now, you're going to see some type of ester in there. Polyol ester, something on that order. Diverse lubricant applications dictate the need for a variety of different base materials. So these are going to change. Broad range of stocks are available in each group. Esters, for example. I just mentioned 3 types of esters that are out there. There are more. And then they're available in different viscosity or thickness grades too. So it's not like, oh, it's a synthetic. All synthetics are the same. Nothing could be further from the truth. Nothing could be further in the truth. And like I did mention, many lubricants will use multiple base materials in there to get the desired performance categories on there. Common benefits of synthetics: because of their purity, they tend to form less deposits, which can be an issue in a variety of different applications. Compressors come to mind on it. They have functionality over a broader temperature range, great for Arctic conditions, yet they're perfectly functional in the Sahara. Improved wear protection. Because of their ability to maintain their viscosity, to maintain their load carrying ability, they can provide a higher level of wear protection on there. Good shear stability. We talked about that before. They're not as easily chopped up and their viscosity lost on there. Low toxicity. As a general rule of thumb, synthetics do have lower toxicity. They tend to have a higher rate of biodegradability. There can be exceptions, of course, as there are to all rules. Okay, there are some synthetic base materials out there that tend to be highly toxic, but generally speaking, they have low toxicity on there. One of the big things is, because the raw materials are uniform, whereas I mentioned when crudes, their makeup varies depending on where it originated. Okay? Because the makeup is going to vary when they are subjected to the refining process, the end product is going to have some slight differences in consistencies, properties, performance, and that type of thing. We don't have that when we look at synthetics. We know before they're made exactly how they're going to function, what they're going to do, what they're not going to be able to do. We know all of that and how well they're going to be able to do these things. We know that ahead of time on it. Biodegradability in synthetics, I'll be the first one to tell you, their initial cost is high. But in many, many, many cases, if you look at the cost of use, their cost is significantly lower than utilizing a cheaper mineral oil. When we get back to the synthetic groups and the different, we had mentioned that Group 3 actually started out as a byproduct of crude oil, okay? And you say, well, is that still a mineral oil? Well, again, by definition, no, it's not. It has been changed significantly to be classified as a synthetic. How close does it come to other more conventionally generated synthetics? Well, here's kind of a good example. Saturation, molecular structures, not quite as uniform as we find in the synthetic. Aromatics, that's the type of molecular structure in there. You're going to find some in the Group 3. POs should virtually have nothing in there. Aromatics are undesirable because they really don't possess the lubricating properties that we're looking for. From a contaminant level, PAOs are none. They're perfectly clean when it comes to sulfur on there. Though a PAO, Group 3, depending on how it was generated, could have some residual left in there. Viscosities, PAOs are available in a much wider range than group 3s are. Matter of fact, when you look at group 3s, you see they're basically only available in up to 8 centistoke base fluid, the thickness on there. That in itself would not be thick enough to formulate like an SAE 30 or an SAE 40 engine oil. You'd have to do something with them. And chemically, you can put in chemical compounds that will allow you to safely do that. They're basically called viscosity index improvers. All right. The only thing is, if you take a look at a PAO, we can formulate these heavier oils without the need for that chemistry in it. So there can be certainly advantages because using a PAO would give you a much more shear stable product, something that's not likely to thin out as readily when exposed to shear stresses on there. Viscosity indexes, again, they're pretty much the same on there. Some of that is adjusted through the use of additional chemistry. A big issue, however, is low temperature performance. Synthetic PAO is going to function at significantly lower temperatures than even a group 3 is going to. So there's a big advantage there. PAOs, group 3s have come a long way to bridge the gap from conventional mineral oils to synthetic. A long way. But are they there all the way? No. They do still fall a little short in some areas. And consistency, we talked about being one. Here is a comparison, same type of GC comparison, but what we've done is compared that group 4 PAO on the right with a typical group 3 synthetic. You see in the comparison here, they pretty much cleaned those or got the light fractions out, but still run into a little too much heavier fractions remaining in there. So that's why there's a difference on it. How big is this difference? One of the other drawbacks of group 3s is their performance is varied by the manner in which they were produced, what type of refining processes they were exposed to. And hence, what that does is, though PAOs are very much the same regardless of how they're obtained, group 3s are not. They will vary from one supplier to another, again, depending on how they were actually manufactured. How much difference is there? Depending on the characteristic, in some cases not much. In this case here, we're looking at low temperature properties on there. We see 4 different group 3 bases from 4 different manufacturers, and you can see there's some variance. In all cases, however, the low temperature performance of the group 3 are not as good as what we find in an average PAO. Moving on from there, volatility. If we don't have the light fractions in an oil, we're not going to have as much volatility. So we should be able to see a similar variance between the two. PAO is far less volatile. And we can see a variance between in volatility depending on where the product was actually manufactured. Some other changes, oxidation stability. This is absolutely critical when we look at the severity of today's automotive technology, the stresses that the oils are being exposed to nowadays. A huge difference in the oxidation stability in the group 3s. PAOs, again, generally are significantly lower. are significantly better when it comes to oxidation stability itself, allowing for less oil thickening, a longer engine life, and certainly a greater safety margin. Another key thing, and I should have brought this up before, when we look at advantages of synthetics, they provide you with this safety margin. For the average consumer, are you going to go run out and immediately change the oil in your car as soon as the change oil light comes on the dashboard? No. When are you going to do it? The next day? Boy, that'd be nice. Hey, next day I can't. I got to bring my daughter to this Girl Scout. I'd like to do her the day after that, but I'm going golfing with the next door neighbor. You know, all of a sudden it's a few days down the road, then it's a week down the road, then it's a month down the road. Well, the engine told you to change the oil. They want you to change it. You have very little safety margin in there. Synthetics provide you that safety margin, so if you run into a situation, if you have to go a little longer, it's not going to be a major issue. Coefficient of friction, traction coefficient I should say, certainly much better than all of the Group 3s, but we can see that there is a variation in there. Group 3s, again, they're bridging the gap between mineral and normally what we refer to synthetics, but they're not quite there. A lot better than mineral, but there can be room for improvements. Okay, why do performance variations occur? We've kind of talked about this too. The difference in the raw materials, the crude oil, depends on where it comes from, because the makeup is going to change on there. And the actual refining process that these raw materials were exposed to on there. How do you know if I'm, or what I'm getting when I buy a Group 3 or a Group 3 product? I tell you what, you can take a look at some of the technical properties and data sheets on that. Take a look at low temperature performance, that's usually an indicator. Most of the other things are not going to be not very clear. A big indicator is cost. When it comes to Group 3s, you get what you pay for. You're not going to be able to get a good Group 3 for $1.25 a quart. You know? You're going to pay for a good one, you're going to pay money for it. Very close to what you'd pay for a PAO. Going to be less expensive, but you kind of get what you pay for. Cost is a real clue on there too. Our particular base materials, highest quality. We've always talked about quality being the number one issue with us. Low volatility to ensure minimized oil consumption. Stable viscosity. By maintaining a good viscosity characteristics, we're going to be able to minimize wear to a greater extent on there. We use stocks that are thermally stable, so they're going to be able to resist resist high temperature degradation significantly better than the competition. Again, oxidation resistant. If these can withstand these higher temperatures, there's less sludge and deposit formation, less oil thickening that's going to occur on there, and certainly it's going to extend the service life of the oil itself. Natural high viscosity indices on it. So we know right off the bat they're going to have an ability to function over a broader temperature range and protect over that broader temperature range. They're not going to thin out at high temperatures when the going gets tough and lose their ability to carry a load. Big thing, big takeaway here is not all synthetic oils are created equal. Also too, here's a good comparison here of deterioration or change in properties due to use or deterioration during use. We've got 3 examples here. I know you've seen this before. This will give you a little more insight onto it. The first one's a PAO, second one's a Group 3, third one's a Group 2. Okay? What we did is we put them in a simulated engine test for 300 hours. All 3 are 10W30 engine oils. All right? All 3 qualify new as a 10W product. But what happens when they're exposed to use? The PAO, after 300 hours of use, did thicken up a little bit, and now only qualifies as a 15W product. The PAO, the group 3 and the group 2, the mineral oil, actually failed. They thickened up to the point where now they failed to meet any API winter service category. That's through use. Again, has a lot to do with its oxidation stability. It's going to thicken up, and these are the types of situations that you can have. In this type of case, the group 3 and the group 2 product would be totally unable to function in a normal wintertime environment. And that's after 300 hours. The group 2, by the way, that actually failed after 15 hours. Kind of bit the dust real quick. So much for thermal stability there. And this was some of the stuff. Lack of performance here, startability problems, poor or lack of oil circulation. Another thing, even if you're not dealing with cold climates, this thickening oil is going to cost increased energy consumption. Your fuel economy is going to go to heck in a handbasket. Big thing there. Loss of engine performance. Hey, if you're not circulating the oil, good chance there's going to be an engine oil or engine failure. And it's certainly going to shorten the life expectancy of the equipment itself. General comparisons between these two, again, Group 3 oils can offer vastly improved performance over conventional Group 1, Group 2 stocks. They can, absolutely. Can be a good way to go. Properties of the Group 3 oils can dramatically vary depending on where they're obtained from, or where they are obtained from. And that's both where the raw material came from and the refining process that it was exposed to. And the price, depending on those variables, is going to change and can change dramatically. As a rule of thumb, the more expensive it is, generally the higher quality it is, it'll perform at a higher rate. POs still have advantages, over the Group 3s, greater consistency in content and performance, improved, expanded high and low temperature protection on there, greater energy efficiency, better fuel economies, what we're talking about there. If you can control wear better, you're going to have longer equipment life. If you can control oxidation better, you're going to have longer service life of the oil. And PAOs do have a greater ability to reduce the overall cost of operation of a piece of equipment than the Group 3s do. Okay, again, no base stock group provides the best performance in all areas. And because of the diverse demands that applications place on base stocks, we're going to have to, or you're going to seriously have to look at the use of multiple types of stocks. And in some cases, it may require oils with more than one base stock in them. Today's challenges, we've already talked about them: higher operating temperatures, higher operating speeds, higher bearing loads. We're looking for improved energy efficiency, going to lighter weight oils, that type of thing. Emissions have placed a lot of additional strain on the engine oils themselves, and even after all these problems, we're saying we want that oil to remain in service longer. You know, it's like, how much can you beat me up? But that's what's being required, and the only really way to go with that is utilizing base materials that can perform at a higher level. Crude oil, mineral oils are going to be around for a long time to come. There is a place for them, okay? Performance demands on can accommodate. And you're going to see more and more original equipment manufacturers not only recommend but demand the use of a synthetic oil on there. As the need to increase the cost of operation and ownership continues to become more and more of an issue, you're going to see synthetic alternatives become more and more of a desirable alternative, and certainly in greater demands. Those synthetics that currently only make up probably 5% of the market at most, when we look at mobile transportation on that, that certainly is going to grow dramatically over the course of the next few years. And with that, I thank you for your time.